Good morning, guys. Problems, questions, observational remarks? Everybody silent. Good news. Last lecture was the most difficult and full of calculations lecture. It was the top. Now, today it will be easier. And last time we saw how to analyze, in general, with a very generic, a very systematic method, how to analyze from the dynamic point of view the topologies, or even more. And the basic idea is to write down the differential equations in a matrix form for all these circuits, and we had to write down all the circuits and the Chuk and the Zeta and Sepic and whatever, and the Weinberger and whatever you want to add. And we had to write down two sets of differential equations, one for D, one for 1 minus D, and then average them. That is an approximation. The average is not exact, but it's good enough. If we are in DCM, we have to write down 3 sets of differential equations for T1, T2, and T idle. And we have to add an extra auxiliary equation, because in DCM we don't know how long is T2. We only know T1 because we control it, but we don't know T2 and T idle, so we have to add an auxiliary equation. It's a little bit longer, we need more calculations, but the idea is still the same. And you could use the state space averaging over here. State space averaging is a method that is very heavy, full of calculations, a lot of algebra. First disadvantage, because you write down the equation for the full circuit, for the complete circuit, and then you average it. But you don't need to write down the equations for it and to average this inductor, because an inductor is linear time invariant element. You don't have to write down the equation for the capacitor, because the capacitor is linear time invariant. The only bad guys in this circuit are switches. Nevertheless, that was the first idea that came out in the mid-70s, late 70s, and it was a great idea because for the first time designers could have an idea what was the transfer function without having to guess or to have to trying to stabilize the system. Using the state space averaging is in some way like having circuits taken in transistor circuit, like for example this circuit. And if you want to solve this circuit, to find the gain from here to here or whatever you want, you write down the complete Kirchhoff equations for this circuit, including the nonlinearities of the transistor. The transistor has an exponential nonlinearity, and then you try to solve this set of equations, many equations, nonlinear, etc. That's not a good, smart idea nowadays. It was a smart idea as soon as they invented the transistor, but not nowadays anymore. And the basic idea to solve this circuit for the gain is remove the nonlinear element, a difficult element to deal with, and substitute it with its linear equivalent circuit, if you linearize in a given point. So you put here the equivalent of a transistor, and you solve it with the standard techniques. You first work on the nonlinear element, and then you work on the other circuit. And we can do the same for our switch mode converters, because the only bad guys, the only components that give you troubles, because they are time variant, because they introduce a nonlinearity, the bad guys are these two. Just these two. Everything else you can add after you linearize, you average and linearize these two switches. And look at what's interesting. These two elements have one common point. And if you look at what topology is this? Boost. You find the same set of components. You find here is the same set of these two components with the same connection, because you have diode and switch connected in one point, and then diode going somewhere, and the switch going somewhere else. And here you have diode and the switch connected together, and then the diode goes somewhere and the switch goes somewhere else. And here for the buck boost, the same story. You still have the same tripole, the same time variant tripole. That is one here, and one here. If it was a transistor, we would call it base collector emitter or source gain drain capacitor. Here is not a transistor, but it's still the same circuit. You have the same time variant, non-linear piece of junk that goes from, that's not a piece of junk actually, it's an important point, it's a helpful point because those are switches that you don't lose, they don't waste power, but you have the same difficult to handle circuit that goes from one topology to another one. I forgot to draw the two converter, but in a two converter there are still these two elements connected in the same way as a tripole. And so, instead of analyzing all the circuit together, and if we change the topology, we have to restart from the scratch, writing down matrices, equations, and so on. We could analyze first, we could work first on this tripole. We analyze this, we average it, we linearize it, and then once that we have it linearized and averaged and linearized, we can substitute, put this the model of this circuit here inside, here inside, here inside. Exactly as in a transistor, you derive the small signal model for a transistor, and then you can put it in a common base, common emitter, common collector or circuit. It's exactly the same idea. So we have first to work to average, to linearize this set of components. Because those are the only components that are time variant. Those are the only components that need to be averaged. The other inductors, capacitors, loads, they don't need to be averaged. They are already time variant. So these three elements, this tripole has three poles that are called A for active. This is just a name because it's connected to the active switch, the switch that we control. Here it's called common, see, because it's common between the two switches, and this one is, this is a passive switch, so this pin is called P, and it's passive. So we need to describe with equations this circuit, average it, linearize it, and then with the model, the small signal model we derive from this circuit, we can go to our original switch mode converter and substitute it instead of the switches. Good news. Do you see any element storing energy here inside? Do you see any element that has been described by a differential equation here inside? Do you see any element with memory here inside? No. That means that this system is memoryless. This system does not introduce any pole or zero. This system is not to be described with differential equation. It's not a transfer function. It's just algebraic equations. So instead of using a lot of differential equations, we will use a simple differential algebraic equation to describe this stuff and to average it and to linearize it. This was invented in '90 by Vorperian, and it was a good idea. But it was the second idea. The first who solved the problem of modeling a switch mode converter was Middlebrook in the late '70s, and after 15 years, Vorperian came out with this idea. Because every time you discover something, the first time you write it down, it's not written in the best way, in the more comprehensible way, in the more understandable way that you can imagine. It's the first time. Then people start to analyze it, to study it, to think about it, and people can come out with more easier ways to deal with it. And it's the same story for anything. If you consider, for example, Thevenin equivalent, you know Thevenin equivalent is okay, it's pretty easy. Well, if you read the original paper by Monsieur Thevenin, it was a French captain of the army. It's basically not understandable. I read it. If I didn't know that it was the Trevenant theorem, I didn't recognize it because it was very complicated, written in a very involved way, convoluted way, difficult to read way, and this is the same story. First idea was, okay, it's not a problem, but now we can do better. And by the way, the technique of state space averaging, you don't use it every day because it has been used and applied for all topologies and you have the result. As a design engineer, you just read the result. As an engineer, you need to know where these results come from, but otherwise you don't have to solve this differential equation I wrote last time, unless you are dealing with a very difficult strength topology, and in this case, if nothing else works, that technique still works. So, let's describe this circuit. We need to set a couple of voltages, input and output voltages, to describe the behavior of this set of switches, and these voltages are the AP, because the voltage between active and passive, and the CP, because the voltage between common and passive. And we also need two currents, because this is a double dipole. So we need a current over here, we call it IA, and we have here a current that is IC. I picked the configuration that looks like the configuration of the buck converter. If you want to use these as you want to rotate it by 90 degrees and having these connected to the bottom part and using these two voltages and these two voltages, this voltage VAC and VCP, that's okay. You can analyze, for example, with the same technique, this stuff. This is CP, etc. But it's, that is the most convenient. Is the easiest to handle. So we have two currents, IA and IC, two voltages, VA and VHP and VCP, and we work by now and forever. We work with CCM. This technique, as usual, can be used for CCM and DCM as well. I put on the website two links to the two original papers by Mr. Vorperian, who described this method for CCM, and the second paper is for DCM. DCM is a little bit more complicated, but still viable. And if we are in CCM, we have two phases. The phase is with T on and with T off. And T on plus T off is equal to the switch. So, during T on, that's very difficult, complicated, impossible to write down. The impossible equation for this stuff are that VCP is equal to VAP. So we can write down VCP equals VAP. And what about current? What is during T on IA? IA is equal to IC, because diode is open and switch is closed. So IA equals to IC. And what about during T off? During T off, we have that VCP is equal to zero, because if you observe, one inductor can only be connected to the common. Inductor cannot be connected to the active things, the active because if you connect an inductor in series with a switch, when the switch opens, the inductor gets very mad. So the inductor can only be connected over here. VCP equals 0, and IA equals, when the switch is open, 0. Just observe that here I put on the left hand side that VCP, that is the quantity that goes to 0, during T off, and here I put to the left-hand side of the equation IA, because it's the quantity that goes to 0 during T off. If you write IC equals IA, for a mathematician it's okay, for an engineer it's not okay, because this is not an inequality expression, this is an assignment expression. It says that IA takes the value of IC. It's like in any programming language. In C, you write this with an equal, not double equal. Okay. Complicated equations? Yeah, very much. Can you imagine how to average these two sets of equations? Yes, straightforward. Well, it's straightforward, let's use it, let's do it mathematically, because there is a small critical point under the fact of averaging these two equations. Let's define, I like when we introduce auxiliary functions. Let's define a function of time qt that is equal to 1 unit t on and is equal to 0 unit t off. It's a square wave. It's a square wave like this. This is qt. This is t on. This is t off. And this value is 1, this value is 0. It's just, it's called switching function. It just describes if the switch is open or the switch is closed. So we can merge that two equations in one equation only that says that VCP equals VAP times Q, and IA equals IC times Q. VCP, VAP, Q, all the variables in this equation are a function of time. VAP can change in time. Q changes in time. Well, it's a square wave, but it's a T on and T off phases can change in length. So those are just the simple time domain equations, algebraic equations. Can we average it? Because I want to average. Why do I want to average?
You want to give the equation function.
We want to get rid of switches. We want to get rid of discontinuity. We want to get rid of topology changes. What do we lose when we average? Big values, RMS values, waveforms, everything that happens inside one cycle. What else do we lose when we average? Frequency domain up to or above switching frequency over 2, because it's a sample system. Or if you consider the moving average, it's the same story. We just cancel the switching frequency and all it's harmonics. So let's average this stuff. We take the average, and average means that VCP average equals VAP times Q average, and IA equals average equals IC times Q average. And now the tricky part, the difficult part, the part that could give me troubles. I would like very much to split this average, the average of the product to be equal to the product of averages. I would like very much to write down that VCP equals VAP average times Q average. And I would like very much to write down that IA average equals IC average times Q average. Is it true? Is it right?
Not always. Not always.
Not always. Let's say very right, it's right. When may I do this operation? When this is legal, when it's right, mathematically speaking.
When one of the two is constant.
When one of the two quantities is constant, there is one extra, and this is not our case because both Q and these quantities change, so unfortunately it's not true. What else?
They are independent of each other.
When those two variables are statistically independent, I cannot guarantee that this is statistically independent. Or the statistic independence, you can check it using the integral. You make the integral of the product and you check if it is 0 or not. But there is another way to check if two variables are statistically independent, and it's looking at their Fourier transform, the spectrum. If one of two variables has a low frequency spectrum and the other variable has a high frequency spectrum, these two spectra are separated. They are not interrelated, they are not overlapping. And so if the one is a low frequency signal, the other one is a high frequency signal, you can say that those are statistically independent. This is almost the case over here, because Q is a signal like this, high frequency. This is within one cycle, IC does not change too much because IC is the current to an inductor. So you can say that those are probably not really statistically independent, but almost statistically independent, because those are two different. They have two different spectra. You can say during one cycle, the signal Q changes because it goes in one cycle goes from 0 to 1. During one cycle, VAP or IC don't change so much, so you can say that this is almost a constant quantity with respect to the Q. So this is an approximation, but it's a reasonable approximation for our circuit. Because in our circuit, we know that in one cycle, inductor current does not change too much, and the input voltage or output voltage does not change too much. So, we can go over here. We have that VCP, just rewriting the same equation, VAP times QT, average, IA, equals IC times Q, average. What is the average of Q? D, duty cycle. So these equations become VCP average, and from this point on, I will assume that everything is average. I will neglect to write down the average sign, equals VAP times D, duty cycle, and duty cycle is a continuous variable going from 0 to 1, and IA equals IC times D, average. Linear or non-linear equations? Done before. Those are non-linear equations because IC, the average of IC changes. For example, the buck converter, IC depends on the average of IC depends on the output load. VAP in a buck converter is the input voltage. So if the input voltage changes, VAP changes. The average of VAP changes. T is the duty cycle. The duty cycle changes. I should write down if I wanted to make this point clear that this is D function of T. This is D function of T. So this is a non-linear equation because I have the product of two variables. But this is a constant. a timing variable. There are no more switching functions. There are no more switches that closes and open. So far so good? Did you already see these equations? Not exactly with those names, but very similar equations.
In the small signal model, we see similar product that we neglect for the.
No. Let's see. We have an output voltage equal to the input voltage times a coefficient. And we have the input current equals to the output current multiplied by a coefficient. What's that? No. That's a transformer. A very strange transformer, a very weird transformer, a very unusual, uncommon transformer. But those are the equations of the transformer. So, for that circuit, we can have, and this is a very good advantage, a very big advantage with respect to the state space averaging, we can write down an equivalent circuit. Not only the equivalent equation, these equations represent something that we understand better, at least I understand better. It is a transformer. And this is the thing A, this is the thing C, this is the thing P, and P, because these two are connected together. I started with the tripole. And the transfer ratio, the turn ratio, even if there are no turns, the turn ratio of this transformer is 1 to D. This is a very magic transformer, because this transformer has a turn ratio, a transformation ratio that is variable, changes in time, can change in time. And this very magic transformer can also transform the DC quantity. So don't go to a transformer manufacturer asking him or her to wind up a circuit like this, because it's impossible. But for analysis purposes, this is a transformer. It's a very magic transformer that can transform the DC as well. It's a transformer that has a different transfer ratio that changes with time, but it's a transformer. It has the same equation of a transformer. For a circuit guy, this is very easy to understand. You can put in a circuit. You can put this transformer into SPICE. You can use SPICE for non-linear model of average circuit. That is exactly what I have to do this afternoon. I'm designing a converter these days, and I made all the power design, that means stresses, speed currents, etc. Now I am worried about the stability of the model. So I don't like to carry on all these time-changing voltages and currents in my average. I just need the average. I just need the non-linear average to see how much time does it require to come out from large stresses or large changes in load or input voltage. So this can be put in SPICE. Okay, SPICE is not this model, but you can model this circuit in SPICE with, for example, two control generators. This is A, this is C, this is P, and this control generator is equal to VAP times D, and this is VAP, and this current source is equal to IC times D. So this is the model of an ideal transformer that you could put in SPICE, and SPICE simulates your circuit using these two controlled transformers faster than simulating your circuit with the switch that closes and opens every cycle. When you use this average model in SPICE, SPICE runs at least 3 orders of magnitude faster. And it's non-linear, so you can see what happens when you have a large change in the output current, for example, and the input voltage or things like this. You see if your loop is stable for any condition, etc. Time domain, non-linear. And to do this, you need to use the transient analysis SPICE. If you give this model, you put this model in your circuit for in SPICE, and you ask SPICE to perform, to carry out an AC analysis, frequency domain. SPICE does it for you. SPICE first linearizes these two non-linear elements, that means around the duty cycle, the constant duty cycle, and makes a small change. And SPICE can also find out the transfer functions just by linearizing these two elements. SPICE can linearize elements. So this is a very powerful from the dynamic point of view, also for simulation, SPICE simulation. And this method has this big advantage with compared to the state space averaging, because state space averaging, I wrote down a ton of equations, but no circuit. I want to see you placing those equations I wrote down on Tuesday in a SPICE. The only way to solve this equation is solve it mathematically. if you are lucky, you have MATLAB, but there is no circuit representation. Well, Vedder tried to find out, to derive a circuit representation of these equations. He did it, but it was a circuit that was basically useless. It was not obvious. Here, if you use this equivalent circuit inside a buck, inside a boost, inside a buck boost, you still see the buck, the boost, and the buck boost. Instead of the two switches, you have this block, or you have this block. I do prefer this one if I am working with my paper and pencil, and the Spice obviously prefers this version. Okay? So far so good. Linear or non-linear? Linear or non-linear? Linear or non-linear? Non-linear, obviously. Is it a problem for Spice? No. It's not a problem, and this is very easy to, very fast to simulate because it has no changes. There are no switches. Time varies or timing varies? Timing varies because we got rid of switches with the average. Our average is critical because we needed to split the average of product into product of averages. That is critical. But it's okay for switch mode power converters. So we have these nonlinear equations. What's the next step? Linearize them. What is the advantage of linearizing a set of different nonlinear equations? What are the disadvantages? What do we lose and what do we get when we linearize?
You can study it in Laplace transform linearizing it.
Linearized system can be analyzed using Laplace transform. It's something, a tool that all engineers know very well. What is the disadvantage of linearizing a system?
We study on a point.
We study on the point.
Loss of generality.
Loss of generality, because we have a space where our converter can work with a very wide range of input voltage, a very wide range of output load. We just pick one point and we study our system with that point and a small circle around that point. It's a small signal. It's called a small signal. Without a small signal, we can't linearize. We will find exactly the same result we got from the state space averaging, but 10 minutes. I still have to linearize this, but those are piece of you can give to the elementary school, to an elementary school kid that he or she can linearize. And to linearize this equation, we use the same technique we used last lecture. That means each variable, each time varying variable, all are time varying, are written as a DC part plus a signal part. So, for example, the AP average. From this point on, I will forget to mark average, but we are in the average domain at this point. The AP average equals the AP capital, that means the DC component of this voltage plus a small change around the DC point. And we write it, we call it VAP hat. And we have to guarantee that VAP DC component is far larger than the AP hat. And this is the same for all the values. So VCP will be equal to VCP DC component plus VCP hat. And IA average will be equal to IA DC component, this average the DC value, its average a constant part, plus IA hat. IC, should I write down all these equations, all these expressions? IC hat, okay, I'm almost done, equals IC DC plus IC hat, and am I done? V, sure. V, that is, this is a number that goes from 0 to 1. It's a function, a continuous function, continuous time function, 0 to 1. It's not Q. It's not the square wave we used at the beginning. D equals D plus D hat. And we substitute over there, and we just make some simple middle school algebra. And I can write that BAP capital plus BAP hat equals BCP plus equals VAP capital plus VCAP hat plus, no, times capital D plus D hat. And the second equation with IA DC component plus IA hat equals IC plus IC hat times D plus D hat. Oh, if I made any mistake on the subscripts, let me know. And linear or non-linear? Non-linear. Now I can separate, as I did earlier, I can separate the DC component, the DC part from the varying part, from the signal part. And so the DC part is just VCP capital equals to what?
VAP times D capital.
VAP times D. And
DC times D equals to
IA equals IC times D, everything capital, because I am just dealing with the DC component. What's that? Those are equations, linear or non-linear? Linear. What circuit do they represent? This is a transformer. A, C, P. This is a magic transformer that can transform also the DC components. And what's the term ratio, transformation ratio?
1 to D.
1 to D. Variable or constant? Constant. So this is just basic component we would like to have. This is a standard, you can see. Transformer. This is DC. Or linear because it has a constant to the side. Okay, we will use it in a moment. We will use it during the oral exam sometimes, because there will be a question using this model. What is this DC component, DC model used for? What could be it used for?
To find the equation we already found.
To find the equation we already found for the M coefficient, or to find the equation for M for a topology that you never saw. There are 3 or 4 more topologies, that basic topologies, simple topologies, I could ask you, and sometimes I ask you during the oral exam, to find out, using this technique, the DC value, the DC n factor for those topologies. I don't ask you to find the AC transfer function because it's very hard. It's not difficult, it's just long, lot of calculations. Now let's go for the AC expression. AC expression equals something like this. We consider this V CP hat. What is VCP? Well, it's a voltage. It's a voltage on the things that's common and passive. But what does it mean? What does it represent, this value? Small change, small variation of what? Of the average output voltage value, output CP value. So remember here there are 2 elements in this symbol. This is average. We are dealing with average. We are not dealing with the square waves anymore. And small changes of this DC component, AC component, this average component. This is equal to VAP hat times D capital plus D hat times VAT capital plus what else?
V times VAT.
VAT hat times V hat. And here we have the very same equation, IA hat equals IC hat times big D plus D hat times big IC plus IC hat times V hat. Very difficult algebra. Linear or non-linear set of equations.
Now, yes.
How can we linearize it?
Neglecting the second order term.
We can neglect the second order terms. Under what assumption, under what conditions can we neglect these second order terms?
They are very small. They are very small. Respect to the DC.
The average, the small signal, the signal that changes is small with respect to the large, to the DC component. So, if we have the small signal approximation, these two terms just move away. What are we left with? Linear or non-linear? Linear. Yay! And these linear equations have a very interesting representation, circuit representation. Okay, let's just consider the first part. What is this first part? Just for a moment, disregard that is the standard, our normal transformer. And our transformer is something like this. Here we have VCP hat, C, this is P, this is P, this is A, and we have here VAP hat, and then we have here IC hat, and we have here IA hat. What's the transformation ratio of this transform?
1 to D. 1 to D.
1 to D. Capital D or small case D? Capital D. It means that this small signal transformer works with a constant duty cycle, with a constant D factor. Linear or non-linear? This transformer. Linear. We linearize it. But it's not all the story, because we have one extra term for each equation. This equation and this equation. Because at this point, this transformer should be exactly the same transformer we found earlier in fixed duty cycle. We don't want fixed duty cycle. We want to change our duty cycle around the bias point, around the constant DC value of the average value of the duty cycle, in order to find out the relationship between the output voltage and the duty cycle, the changes of the output voltage with respect to the change of the duty cycle in dynamic domain. So using changes in differential equation, moments whatever you want. So we have to add these two terms. Okay, what this first equation represents a voltage. And we are adding two voltages. You see? And adding two voltages means that circuitly speaking, circuit-wise, we have to. What is the operation in circuit that adds two voltages?
Two voltages.
We have to put the two voltages in series. So here, if I want to add this component to the output, we have here controlled quantity, controlled voltage source with the positive on the right hand side, and this controlled voltage source is controlled by what is the variable controlling this voltage source?
D to D. D hat.
D hat.
Yeah.
This is D hat times capital VAP. That's capital. And what about the second equation? We needed to add current. And in order to have the current, we need to put in parallel. So at the input, we have to add in parallel to the input a current source that sends down this current, and this current is equal to
the capital AC times the
capital AC times
the hat.
the hat. That's it. This is the small signal system, the small signal equivalent circuit for our nonlinear time variant tripole. Linear or non-linear? Linear. Linear means that we transformed the change in duty cycle that originally was changing by transformation ratio into two added controlled generators. If we change this duty cycle, the system is non-linear because we have the product of two variables. But we split this product into 4 terms. We neglected the second order terms. This is the small signal approximation, this is small signal limitation. This is the fact that we are just working on one point and a small area around that point. And we transform this nonlinearity into the sum of 2 linear terms. Okay? So far so good? Did I derive this model from what topology? From no topologies. That is just the time varying set of switches for any converter. This applies both to buck converters, buck boost converter, Q converters, septic converter, zeta converter, inverse zeta converter, etc. I think Weinberger is not working with this. There's no way to get this tripole. Okay, so far so good. This is valid for any topology. Let's just check if it's okay or not. Let's just make us a quick check. Let's analyze the DC behavior of, tell me any topology but buck is switch. Buck boost, let's go for a buck boost. Buck boost is something like this. Rating LC V out. I want to find out what is N equals V out over V in CCM, because that model has been derived for CCM. It could be derived from VCN, it requires some extra steps. I don't want to do it over here. We will derive the transfer function of VCN converters in a different way. I want to find out this N DC only, because AC is just requiring a lot of algebra in a buck boost converter. So here there is the A pin, this is the C, and this is the B pin. So my idea is, instead of these 2 switches, I put its time invariant model and see what happens. So I can put the transformer over here, A, C, T, and I go around this transformer to connect everything else that is in our original circuit. I do it only for DC. For AC is exactly the same. Here I should use, I should add 2 extra controlled sources, and this is 1 to D. Okay, what is the inductor connected? Inductor is connected from C to somewhere else. So this is F. Then I needed this node. So this is the reason why I started with the inductor. Where is the input voltage connecting to and the input capacitor connecting to? Input voltage and input capacitor are connected between A and the other side of the inductor. So the input voltage is connected from here to here with positive on one side. Left side, this is V in, and there is a capacitor in parallel with this voltage source, but the capacitor in parallel with the voltage source is useless. But if you want to put it, be my guest. Where is the load and the output capacitor? Where are the load and the output capacitors connected to? Between P and the other side of the inductance. So here I have the output capacitor C0